Hello. So, we will discuss the least upper bound, greatest lower bound of a set and compact sets today. So, this requires the concept of ordered set. Ordered set first. We define like this. Let S be a set. S be a set. An order on S. An order on S is a relation denoted by sign, this sign, which we call later on we will say less than sign or smaller sign, with the following two properties. The first property is that if x is in S and y is in S, then one and only one of the following statements that is x is less than y, x is equal to y and y is less than x is true. And second one is, say, if x, y, z, they are the elements of S, and if x is less than y and y is less than z, then x must be less than z. So, if a set S together with this operation, which we call it together with this relation less than sign, satisfy these two property, then we say that this is an order on S. This is an order on S. This sign less than sign, we normally say x rated to the means x is smaller than y. X is smaller than y, and the negation of this is x is greater than or equal to y. This is the negation part of it, means x is greater than or equal to y. The negation of this will be x is strictly less than y. So, that will be the sign for them. Now, obviously, when we say the set of rational number or set of the real numbers, then this order is defined. One can identify two real number or two rational numbers. One can say which one is smaller than the other, or whether they are equal, or whether one is greater than the other, like this. Then the set order set means a set, an ordered set S, order set is a set S in which an order is defined, For example, set rational number, set of all rational numbers is an ordered set. Because if we take R and S, suppose these are two rational number, and define the relation R is less than S, means S minus R is a positive rational number, then obviously it will satisfy these two property which we have stated. So, set of rational number is an ordered set, set of real number is an ordered set, set of real number is an ordered set, ordered set. However, set of complex number, set of complex number is not an ordered set. We cannot introduce the order between the two elements of a C complex number, set of all complex number, because for example, if suppose I take the complex number E and 1, okay, and when we say E is greater than 1, okay, E is the element say square root of minus 1, this is E, or I will say I, if you I, this is a complex number. So, I is greater than 1, it means it is positive we are assuming. So, I into I is still greater than 1 into 1, that is I square is minus 1 is greater than 1, which is a absurd. It means our ordering which you have introduced is not correct. Similarly, one can show whether if I is less than 1, we can again lead a contradiction and like this. So, we are unable to introduce the order in the over the set of all complex number, that is the set of a complex number is not an ordered field. Field we will discuss in algebra or some. Okay. Then we are interested in particular in defining the least upper bound and the greatest lower bound. So, let us see first what is an upper bound and lower. Suppose S is an ordered set, S is an ordered set and E is a non-empty subset of S. Now, if there exists some beta, there exists a beta in S such that all the elements of E, that is x belongs to E, is less than or equal to beta, and this is true for every x belongs to E. Then we say E is, then we say beta is a or E is bounded above, E is bounded above, okay, and beta is an upper bound and beta is known as upper bound for E. Now, obviously, beta is an upper bound, there are many infinitely many real numbers will be available which will be an upper bound for E. Any number which is greater than beta will act as an upper bound for E. Okay. So, we are interested in the least upper bound for it. The same case happens if it is lower bound. We define the lower bound in a similar way. Suppose S is an ordered, suppose S is an ordered set, and E is a subset of S, non-empty subset of S. If there exists a number say gamma belongs to S such that gamma is less than equal to x for every x belongs to E, then we say E is bounded below and gamma is the lower bound is a lower bound of E. So, there again there will be many lower bound available as soon as you take any number less than gamma, which will also behave as a lower bound. So, we will be interested in knowing what will be the greatest lower bound of the set E. So, we introduce the concept of the upper bound and lower bound as follows. This is the concept of least upper bound. Okay. Suppose S is an ordered set, S is an ordered set and E be a non-empty subset of S, and also assume E is bounded above, E is bounded above. Now, suppose there exists an alpha belongs to S with the following property. Alpha is an upper bound of E. This is the first property, and second one is if I take a number slightly lower than alpha, then it should not behave as an upper bound, and second is if gamma is any number less than alpha, then gamma is not an upper bound of E. Okay. So, E is a bounded above and alpha is such a number which is an upper bound of this, but if we take a number slightly lower than alpha, then that number will not behave in upper. It means, alpha is the least upper bound for E. Then alpha is called the least upper bound of E, and we denote this thing as, and also or some we also say it is a supremum of E. And we write that least upper bound of set E is alpha, or it is the same as when we say supremum of E. The similar way we define the greatest lower bound. In a similar way, we can introduce the concept of the greatest lower bound of E. So, what we assume is, suppose S is an ordered set, S is an ordered set, E is a subset, non-empty subset of S, and E is bounded below, below. Suppose there exists and say beta belongs to S, a beta belongs to S with the following property, with the following properties. The first is beta is a lower bound, of E, Second one is, if a number, if I choose, if a number say delta which is greater than beta, then delta is not an is not a lower bound of E, is not a lower bound of E. Okay. So, if we take any number delta slightly higher than this, it will not be lower bound. Then this beta, then beta is known as greatest lower bound of E, or we can also say it is the infimum of the set E, and we denote this as beta is the infimum of the set E, or is the same as the greatest lower bound of E. So, this is the way we define the greatest lower bound and upper and the least upper bound, greatest lower and least. Now, let us take an example. Suppose I take the set A, let A be the set of all positive rational number P. P is positive rational number. So, it is positive rational numbers such that P square is less than 2, and let B is the set of all positive rational numbers such that P square is greater than 2. P square is greater than 2. Now, if we look at A and B, A is the set of all positive rational number whose square is less than 2, and B is the set of all positive rational number whose square is greater than 2. Obviously, A is bounded above. In fact, all the elements of B will be the upper bound, will act as an upper bound for A, but A does not have the least upper bound, because we can't get the rational number which is for which we can say is a really a number which is a least upper bound for it. Similarly, for the B, if you look the all the elements of B satisfy this condition, then it has a lower bound, and all the elements of A behave as a lower bound of this plus all rational number which are negative or 0 will behave as a lower bound for this, but neither A nor B has an upper bound and the greatest lower bound. Okay. So, this will show that A contains no largest number and B is clearly A contains no largest number, while the B and B contains no smallest number. Okay. So, in this case the greatest lower bound A has no greatest B has no greatest lower bound and has no largest number. So, this so therefore, we can say A has no least upper bound while the B has no greatest lower bound. That is obviously true. Okay. Let us take another example. Suppose I take the set of rational numbers, let E1 be the set of all rational number R belongs to Q such that R is strictly less than 0, and E2 be the set of all rational number Q rationals such that R is greater than equal to 0. Okay. R is less than equal to 0, same, such that R is less than equal to 0. Suppose I take this thing, then the set of rational number which are less than 0. So, obviously, it has an upper bound 0, here also has upper bound 0. It means the supremum value of E. So, therefore, supremum of E1 will be 0, supremum of E2 will also be 0, but you see the supremum value of E1 does not belongs to E1, while the supremum value of E2 belongs to E. So, it is not necessary when we say the least upper bound or greatest lower bound, then it is not required, it is not necessary that that supremum value will be a point of set. It may or may not be the point of set that we have observed here. Okay. Similarly, but both are having the same. Okay. Similarly, now another interesting property which is in connection with the order set is, this is known as the least upper bound property. Least upper bound property. What is the least upper bound property? An ordered set S is said to have the least upper bound property if the following is true. Following is true. What is the if E is a non-empty subset of S, is not empty, is a non-empty subset of S, and E is bounded above. Then the supremum of E, that is least upper bound of E, will exist and exist in S. So, this is the least upper bound property of a set. An order set S is said to have a least upper bound property if the following is true. That is, if we take any subset, non-empty subset of A which is bounded above, then supremum E exists in S, then we say this set S is a least upper bound property. If for any set this supremum does not exist, then the set will not have a least upper bound property. For example, set of rational numbers, that is which is denoted by Q, does not have least upper bound property. And that we have seen already with this example, because basically A and B, these are the two subsets of the rational numbers, and neither the A nor B has an upper bound, is it not? Neither A does not have a upper bound, B does not have the lower bound for it. So, basically the set of rational number you can say does not have a least upper bound property. Now, there is a relation between the greatest lower bound, least upper bound, and the least upper bound property. In fact, it is shown that if the set is having the least upper bound property, then it must have a greatest lower bound property also, and that can be judged in the next theorem. The relation between the least upper bound, greatest lower bound, and this. So, theorem says, or you can, before this you can write the remark. I will write the remark here is every order set, there is a relation between the greatest lower bound, that every order set with the least upper bound property properties with the least also has their remark is there is a close relation between greatest lower bound and the least upper bound, and that that every order set with the least upper bound property also the has the greatest lower bound property. This can be seen with the help of this result.